Lesson 1.5, the real number system and absolute value. This video is being made of two other videos being strung together from Algebra 1A, and therefore it may not exactly mesh well, and it will mention two other lesson numbers that you can ignore. This is Lesson 1.05 for Algebra 1B. Lesson 1.2, Grouping Numbers. The FATDEC program, our online algebra class, refers to number systems as grouping numbers. And this is pretty accurate because when we talk about number systems, we're talking about the ways that numbers are similar to each other or can be grouped together. I like to think of the number systems as families. There are two main families of numbers: the real number family, which is the set of all real numbers, and the complex number family, which is the set of all complex numbers. Now, we're only going to be dealing with real numbers in Algebra 1. Complex numbers will come up in future algebra classes, but I just wanted you to know that there were two systems. One of the most common ways to classify sets of numbers is the use of a Venn diagram like this. Now, a Venn diagram is just basically a graphic organizer that allows you to arrange items in a way that makes sense. When we start talking about sets of numbers, we're going to start at the smallest set and work our way up to the largest set, which is the entire real number set. The smallest set of numbers are the natural numbers. Natural numbers are also known as counting numbers, and that's because these are the numbers that we use when we count. We start at 1 and we start counting 1, 2, 3, 4, 5, 6, 7, etc. And you can count forever. So the natural numbers are infinite. They start at 1 and go forever, adding 1 each time. Natural numbers are symbolized with a capital N that's bolded. The next set of numbers that we have are the whole numbers. Now, as you can see from the diagram, natural numbers fit inside of the whole numbers, and the only difference between the whole numbers and the natural numbers is the addition of 0. So whole numbers start at 0 and then go up for infinity. So 0, 1, 2, 3, 4, 5, etc. They keep going forever. Whole numbers are symbolized with a capital W that's bolded. Whole numbers fit inside the next number system, which are the integers. And the integers are all of the whole numbers and their opposites. So instead of just going in one direction, 0, 1, 2, 3, and 4, we go in two directions, all of the positive numbers and all of the negative numbers. No fractions and no decimals at this point, just whole numbers that are either positive or negative. Integers are symbolized with a bold capital Z. The next number set that we have are rational numbers. Now, rational numbers are any number that can be written as a fraction. That's the definition of a rational number. They're all of the integers, all of the fractions, and all terminating in repeating decimals. These are decimals that either end or have a repeating pattern. They're symbolized with a capital bold Q. So far, all of our number sets have fit inside each other. Natural numbers fit inside whole numbers, which fit inside integers, which fit inside rational numbers. And the reason this works is because each time we just add more to the set. For example, the integer 2 can be written as a fraction. You just put a 1 underneath it. It's 2 over 1. It's a fraction. That means the integer can also be a rational number. We have another set of numbers, though, that doesn't quite fit into this pattern. That's why you have this rectangle sort of in the middle of the Venn diagram. It doesn't really fit, but it's still a real number. These are the irrational numbers. You may have heard of these before. These are all of the decimals that never end and never repeat. Very famous example of an irrational number is pi. Pi is a decimal that never ends and never repeats. Also, all non-perfect squares are irrational. If you take the square root of 2, it's not a perfect square, you're going to get a decimal that never ends and never repeats. Irrational numbers don't have their own symbol per se. You either take the R for real numbers and subtract Q, which are all of the rationals. So basically, it's every real number that's not rational. Or you can do the Q with a bar over it, which means not rational. All of these numbers together are real numbers, which are symbolized with a bold R. Another way to look at it is through the use of a physical example in nesting dolls.
Okay, a physical way to identify number sets is the use of wooden nesting dolls. Remember I mentioned that I like to think of them as a family? Well, this will be the baby of the family, the natural numbers. It's the smallest set, the smallest doll. Natural numbers fit inside the whole numbers. Again, whole numbers run between 0, 1, 2, 3, 4, etc. Whole numbers fit inside of the integers, which are all of the positives and negatives. Integers fit inside of the rational numbers. Rational numbers are all of the fractions, all of the integers, and all of the decimals that end or repeat. Now, every family has that family member, crazy Uncle Joe, that's part of the family but doesn't really fit. These are the irrational numbers. These are the non-ending, non-repeating decimals, but they still fit inside the real number family.
Now that we've looked at the Venn diagram and the nesting dolls, this is a flowchart system for categorizing the real number system. This allows you to look at numbers and determine sort of where they fit. We have a real number that's either going to be rational or irrational. You have two choices, rational or irrational. If it's irrational, you stop there. That's the only set it would fit into. If it's rational, you have a non-integer fractions, so that's any fraction or decimal. And then you have integers. These are all of the negative or positive whole numbers. If you're a non-integer fraction, you stop there. You're just rational. You're not anything else. If you're an integer, you can keep going. If you're an integer, you're either negative or you're a whole number. So if you're negative, you're just an integer. If you're a whole number, you can keep going. And if you're a whole number, you're either 0 or you're a natural number. So this is another way to kind of categorize or organize the system of real numbers. Now that we've gotten through the categorization, we're going to do some identification. We'll identify the sets to which each of the following numbers belong by putting an X in the box. So let's look at the square root, well, negative the square root of 17. The square root of 17 is not a perfect square. Therefore, when we take the square root of it, we are going to get a non-ending, non-repeating decimal. This is an irrational number. Well, if we're irrational, we're also real, so we can click that as well. Negative 2. Negative 2 is an integer. If it's an integer, it's also rational, and it's also real. Negative 9 over 37, that's a fraction. That makes it rational. It's not an integer, whole number, or natural number, but if it's rational, it's also real. 0. 0 is our first whole number. That makes it an integer, and rational, and real. Negative 6.06, this is a decimal, therefore it's rational, therefore it's real. 4.56 with a bar over it. Now this bar indicates that the decimal repeats. Okay, repeating decimals are rational. They're also real. 3.05005,005 is a repeating pattern, therefore it's rational and real. 18 is a number we can count to. That makes it natural, which makes it whole and an integer and rational and real. Negative 43 over 0 looks like a fraction, but we cannot divide by 0. That's an illegal operation in math. That means that this number does not actually exist. It does not fit into any of the categories. Pi is our famous example of an irrational number, but even if it's irrational, it's still real. 0.634 repeats. That makes it rational and real. The square root of 225 is equal to 15. 15 is a counting number, which makes it whole, an integer, rational, and real. 0.634 is a decimal that ends. This makes it rational, which makes it real. The square root of 4 over 49 is 2 over 7. This is a fraction, therefore it's rational and it's real. And the negative square root of 64 is negative 8. The negative outside of the square root is okay, it just hangs out. Negatives inside of the square root, we don't allow. But it's negative 8. That makes it an integer, which makes it rational and real. Hopefully that cleared up identifying number sets, and you'll do some practice on your own. Module 1.06, absolute value. Let's say you decide to run a mile. You're running forwards, you run 1 mile. Well, let's say you decide to run backwards and you run a mile. Is there any difference in the distance that you ran between running forwards and running backwards? Or did you run a mile either way? You can't run a negative mile. Absolute value is the distance from 0 on the number line. Since distance can never be negative, absolute value can also never be negative. Doesn't matter which direction we move from 0, whether we move in a positive direction or a negative direction, we still move a positive distance. In order to simplify absolute value, we first look at these bars that identify absolute value. You look at the number inside, and the absolute value of a positive number is a positive number. And the absolute value of a negative number is a positive number. Absolute value is always positive. Absolute value is also a grouping symbol. Operations must be performed inside the absolute value bars before the absolute value is taken. So for example, if we have 2 plus 7 located inside absolute value bars, we first add those numbers together, then we take the absolute value of it, which again is always positive. 4 minus 8 inside the absolute value bars, we subtract first, then take the absolute value of it, which is always positive. Here's some more examples using absolute value as a grouping symbol. 2 times the absolute value of 3 minus 8 is 2 times the absolute value of negative 5. The absolute value of negative 5 is positive 5, so we have 2 times 5, which gives us 10. Negative 9 times the absolute value of 2 minus 9 gives me negative 9 times the absolute value of negative 7. The absolute value of negative 7 is positive 7. So I get a negative 63. Now in this case, I got a negative answer because of this negative 9. That didn't change. 4 times the absolute value of 1 minus 6. It's 4 times the absolute value of negative 5, which is 4 times 5, which is 20. If I have 2 absolute values, I take each operation inside and complete those first. Then I take the absolute value of each number Then I perform the subtraction in between. 5 minus 12 is negative 7. 1 minus 5 is negative 4. Absolute values gives me 11. Here are some more problems. Why don't you pause the video, try them on your own, and then come back on it after you've been done, and we'll go over them together. So how'd you do? Combined all of the operations inside the absolute value, took the absolute value to get positive numbers, and then performed the operations, multiplication, addition, and subtraction that were required.